Having on the car, I can make that joke. Okay, before we can talk about the bases, though, we really have to discuss a little bit of what's going on with water first. And that is, water undergoes an ionization of its own. Not a lot of it. Kw is very tiny here, which is the dissociation constant, but it's not zero, and it's going to help us out as we go to looking at the base side of the problem. If we write out an equilibrium expression there, since water itself is not an aqueous solution, and the two ions are, they're going to appear in the expression, water is not. So I'm going to have a term for the hydronium ion, I'm going to have a term for the hydroxide ion, I do not have a term for water. And if you were astute and noticed that wasn't balanced, good. In this case, it doesn't really matter because that doesn't appear in our equilibrium expression, but it still should be balanced all along. So at equilibrium, those two are going to have equal concentrations, denoted here by x. So Kw is going to simplify down to x squared, which gives us the solution x as 1.0 times 10 to the minus 7 molar. For our purposes, that's the hydronium concentration that we normally care about, which means our pH is, surprise, surprise, 7, which you knew is the pH for water all along. But this is how that number came about. All right, well, technically, the hydroxide concentration is exactly the same. But what we really need to do is look at that equilibrium not as coming directly from water, but as being true in water at all times. What I mean by that is if we're talking about something that's a strong acid, it means that the hydronium concentration is higher, but since that's always related at equilibrium through Kw, no matter what the acid is, then the hydroxide concentration has to be lower, and vice versa. So if we're going to look at the basic side of the puzzle, which we are, then generally we're going to be talking about pH. That's the universal scale for acidity or basicity is pH. So we're going to end up solving for a hydroxide concentration, but you can't get to pH from there. pH is the hydronium concentration, so we could put it into this expression and solve for the other one, and then take the negative log of that. Or, alternatively, we could just take the negative log of the entire thing to begin with. So that's going to give me one side that's numerical, which you see on the left, and the other side that has the multiplication actually as addition. The negative signs here come from the original negative log. So what I get if I actually rewrite that is that the numerical side simplifies down to 14. I get a term for pH and a term for what is now called POH. When we're dealing with bases, sometimes it's easier to go through POH and then just subtract that number from 14 to get to the pH, which is what we use for our standard of reporting whether something is acidic or basic. So if I had something like a pH of 2, that means the POH has to be 12 because the two have to add up to 14. If the POH is 6, then the pH is going to have to be 8 because the two have to add up to 14. But what you're seeing is that if I have a really small pH, I have a very large POH, and vice versa. And in pH terms, below 7 is acidic, above 7 is basic. And that's what we're going to be dealing with, is that the POH will be a lower number, therefore the pH will be a larger one up to 14. All right, so now that we got that part out of the way, we have to discuss a little bit about the details of what a base actually is. We had some problems with definitions back in General Chem 1. We said the Arrhenius definition wasn't all that good, so we went with the Bronsted version that a base is only a proton acceptor. So it gets sort of a passive role here in that it just takes. It doesn't actually seem to have an active role the way that the Bronsted acid is a donor that's more of an active. An acceptor just implies passive. That's not true chemically, but that's what it sounds like. The older version, the Arrhenius definition, said that a base was a hydroxide donor. Now, that had some problems with weak bases because they weren't obviously going to give us a hydroxide. Things like ammonia, things like sodium bicarbonate. These are not hydroxide bases. So how do you explain their basic behavior? Back in General Chem 1, the answer is, we'll tell you later. Also known as wait till General Chem 2, we'll talk about that. Well, we can talk about it now because we're looking at an equilibrium. They're weak, so therefore we have an equilibrium very similar to what we saw for the acids. That equilibrium involves water doing part of the job. In the acids, water acts as a base. Water is what we call amphoteric, which means it can be acidic or basic depending on the conditions and what it needs to be. Well, in this case, we already have a base. In this, the one example I'm drawing is ammonia, so water has to be the acid. Well, if water ends up as the acid, what am I left with if it gives up a proton? You guessed it, a hydroxide. So, turns out the Arrhenius base definition is not that bad after all, as long as you're in water. And for the purposes of this course, you're going to be in water all the time. When you get to organic, pH and the water standard kind of go out the window, and we'll deal with pKa more exclusively. We'll talk more about that in the buffers chapter as well, but for now, we can actually go directly to the hydroxide. So if I have this equilibrium written out, I'll have a Kb term. Notice B for base. We had Ka, that was for acidic dissociations. Kb is the basic dissociation, and weak bases will still have a very low number for the equilibrium constant. So this now turns into a very similar problem to the things that we've already dealt with the acids, only we're going to have one extra step at the end, and that is going from whatever the base amount is to a pH value. So here's what that looks like. I'm going to have an initial concentration, I'm going to have my equilibrium expression, and then I'm going to have, as before, the change, which is related by stoichiometry. Usually we just use x for that, so one side decreases, the other side increases by x, and there's no multiples here, so they're all 1x. So at equilibrium, I have an ammonia concentration of 0.13 minus x. The two ions are represented only by x because they started at 0. So my KSP expression is going to end up with the two x's on the top and the 0.13 minus x on the bottom. The rules for neglecting that variable are still what they were for the acids. That was not just an acid trick. It's most useful there because we see those most often. But as long as the concentration is much higher than the equilibrium constant, and in this case it's 10,000 times higher, 10 to the minus 1 for that concentration, 10 to the minus 5 for my equilibrium constant, I can neglect the minus x term. That makes the math a lot simpler. So I end up with just x squared over 0.13 is equal to Kb. So from there, relatively simple, I can solve for x by moving the equation around. I get 1.53 times 10 to the minus 3. All right, I have that as my hydroxide concentration. I need a pH value because that's generally what the question would ask. I can go about that in one of two ways. We're going to look at both of them. First, I can take the Kw expression, which has the hydroxide and hydronium relationship, and Kw. I can put that concentration in for the hydroxide concentration in the expression, and I can solve for the hydronium concentration. If I do that, I end up with an extremely low hydronium concentration. Surprise, surprise, it's a base. We don't expect a lot of acid to be floating around in it. So we end up with 6.5 times 10 to the minus 12. That shouldn't surprise us because, again, we're in basic land, which means less than 10 to the minus 7 compared to what we did at the beginning, which was neutral, the middle point, pH of 7. So now I can take the logarithm of that and change the sign. I end up with a pH of 11.18 or 11.2. That's one way of getting to pH from a basic equilibrium once you have gotten to the hydroxide concentration. The other way is to use that logarithm expression that we talked about earlier, which is that the pH and the pOH are basically just related by the logarithm of the Kw expression. That sometimes is a little easier to do, and it's definitely going to be more common when we look at buffers because we generally have a term that is pH in the expression instead of hydronium concentration or hydroxide concentration. So in this case, the pOH is just the negative log of that initial hydroxide concentration. That is 2.82. That relationship I was talking about, the pH and the pOH together have to add up to 14. So if I have one, I can subtract that from 14, get the other. Unsurprisingly, it's exactly the same number. Okay, now, this is important. Keep this in your brain. The point where we choose to do a logarithm doesn't change the answer I'm going to get afterwards. So the only difference between these two is whether I solve for the hydronium ion before I hit the log button or whether I hit the log button and then solve for the pH, which is the log of the hydronium ion. So it doesn't matter which way I do it. Typically the one on the right is more common because, again, when we do buffers, we have an equation that has pH already in it, or pOH already in it, so the one on the right tends to be a little more common later. But both will give me identical answers because they're identical mathematically. It's just a matter of what steps I'm doing first and in what order.